Hi, welcome back to Fat Mama Physics. This is another power and efficiency lesson, but this one is a continuation of what we were doing before on power. And in this video, I am going to show you how we get this new equation, which is power is equal to force times velocity, as well as applying that in a question. So let's do a quick demonstration of how it can be derived. And I promise it won't be too long. It's okay, it won't be too long. So let's get to it. Okay, so we know that power is the rate of which work is done. So that is work divided by time. We also know that work is your force times a displacement. And let's assume that the work and the displacement are applied in the same direction, and as well as the force, imagine it as some average force. It's the same for, or it's a constant force being applied throughout that displacement, okay? What we can do now is we can then substitute this over here in our power equation. So instead of work, I'm going to put in force times displacement all over the time. And hey, guess what? What's displacement over time? You are correct. That is a velocity. So here we have the force times velocity instead, and voila, here you go. That's how you get that new power equation. But you have to be very careful of when you can use this equation, because this force over here assumes that either it stays constant or it is some sort of average force, okay? So it doesn't change. Same thing with the velocity. You have to assume that this velocity is constant as well. If you're dealing with a question in which either of these are changing, you cannot use this power equation, okay? So it's a very specific case, but if used properly, it can save you a lot of trouble. So let's see how it can be applied. I am going to do example 3, and you will do example 4. So let's get down to it. The vacuum robot, here we got 3.5 grams. Sorry, kilograms. A vacuum robot is vacuuming the floor while moving at a constant velocity. Hey, we like constant velocity. While overcoming a friction force of 12 newtons, what is the power output? And we're talking about the motion. We're not talking anything else like vacuuming and sucking and all that stuff of the robot. Okay, so just talking about motion. To use our power equation, it has to be the force that is used to move the vacuum robot forward at this constant velocity, and which is not the friction force, okay? So we can't just go ahead and use that 12 newtons yet. But we can do is draw a free body diagram to show that. Here we have the force due to gravity, we have the normal force, which we don't really care about, but we do know that the robot is moving forward at a constant velocity. It has a friction force opposing its motion, so whatever force the motors are applying to the robot moving it forward must be equal in magnitude to the force of friction, since the acceleration is 0 in the x direction. So we get force of friction is equal to Fa, which means in our power equation, that is exactly what we can use. And since we have the force of friction, let's go ahead and use that. We get 12 newtons multiplied by the velocity at 0.54 meters per second, and putting that into our calculator, we get 6.48, which then we can round up to 6.5 watts for our energy. Sorry, for our power, okay? So that's our robot. That's how you can use this power equation. Got to make sure you get the right force, make sure it's constant, and make sure your velocity is constant as well, okay? Now, good time to try example 4. What? Hey, isn't that the same question we dealt with before? Well, let's read it first. A 1300 kilogram space elevator was lifted 780 meters up from the surface of the Earth at 2 seconds at constant speed. Ooh, we like constant speed, okay? Calculate the power generated by the space elevator thrust engines. But this time, we must use the method shown above instead. I'm actually going to talk this example through, but if you want to give it a try, this is a good time to pause the video. And now it's my turn to explain. So if we want to use this power equation. Power is equal to the force times the velocity here. We first need the velocity with the speed here, which is constant. That's good to know. We know that the elevator is lifted 780 meters up from the surface of the Earth, and it did that in 2 seconds, meaning we can calculate velocity right now, which is our displacement over time. That's 780 meters over 2 seconds, which then that gives us 390 meters per second for our speed. But then for the force, we got to analyze this one a bit, okay? So we got an elevator. It is moving up. Good thing is moving at constant speed with acceleration of 0. And we have the force due to gravity acting on the space elevator and some thrust engines applied in the upwards direction. So I'm going to use FTH for thrust. Okay, and since it's moving up at a constant velocity, we know that these two forces must be equal and opposite, which means for the power, I do need the power coming from the force of the thrust engines. Since it is equal to Fg, I can use Fg instead. And Fg, we know, is mass times gravity, so let's put that in. The mass of the space elevator is 1,300 kilograms, and gravity 9.81 meters per second squared. And last but not least, the speed, which we just calculated, 390 meters per second. So if we put that all in a calculator, and we really should get exactly what we got in the last video, and voila, we get exactly the same thing, which should be the case, except we're just using a different method. 4973670, which we were going to round to 2 sig figs, so that's 5 million again. 5 million watts. Alrighty. Hey, that's it. That's it for this video lesson. Thank you for watching with me. Hopefully you can use this equation in your own endeavors. Good luck, and Phat Mama Physics signing out.